All right, here we go. Parametric equations. Guys, the idea here, please, the idea is that we're going to introduce a third variable. The trickiest part of today's lesson is going to be learning to use the new features on the calculator. But we're going to start out without a calculator, okay? The idea when we did throw-up problems, where we like threw a ball, we say we threw it up and it came back down and how long was it in the air and all that kind of stuff, because we did quadratic equations. The issue is we were just throwing the ball straight up or dropping it straight down or something. Today we're going to talk about problems where you throw something with an angle to the ground, an initial velocity forward, all that kind of good stuff. Much more realistic, okay? When something travels vertically up over the course of time, we graph it as a parabola. But when I throw something forward, the horizontal distance forward never comes back, right? It just gets further and further away from me, unless it's a boomerang, okay? So it just is linear because it gets further and further away. What we're going to do is we're going to combine this idea. We're going to have a vertical distance and a horizontal distance in terms of time. So at 1 second into its flight, it's this many feet or meters away from us and this many meters in height, and so on. So we're going to have three things we're looking at: horizontal distance, vertical distance, and as those relate to time. For our concern today, we just need to know we're going to have three variables. They're going to give us values of t, and we're going to use a rule they give us to determine x, y's, and plot those. Sounds pretty easy. And then we're going to do some substitution to eliminate those. So a rectangular equation has x's and y's. Parametric equations have x's in terms of a t, which will give us a horizontal component, and y's in terms of t, that'll give us a vertical component. The t is called the parameter, okay? Now, I've never had this issue before, but this is kind of interesting. This book says you actually can specify an orientation of the curve that is based on the t value, and they're going to tell us for a lot of these the t values. Says from 0 to 4. So if this was a time application question, you would say from 0 to 4 seconds, where's this ball at, da 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 da. The orientation part of it just means as you graph from 0 to 4, you put these little arrows on here to show which way the ball's going. Okay? That's the orientation piece. Our old book didn't do that. It's kind of interesting. We'll throw the arrows on. It's not a big deal. All right. This slide says that parameters are arbitrary values, usually time or angle measurement. Today, we're just going to talk about values of t and time eventually. All right, this is the definition of parametric equations. It says you're going to have x in terms of t and y in terms of t, and when you graph it, you're going to graph those x's and the y's that came from that crazy business there. That'll make more sense when we do one here in a second. All right, I'm not going to go through this example extensively, but right here, as part of the original question, it told us what to use for t values. For this question, it said -4 to 4. Now, between -4 and 4, there are infinite numbers. Does everyone understand that? If infinite values, I could put in 0, 0.001, 0.00001. I could put in 0.5. To come up with an estimate, we're just going to put in the whole numbers, or integers, positive and negative, from -4 to 4. Then we're going to put those t values into this rule and come up with x's and y's, and then we're going to plot the x's and y's. The interesting thing is, you will notice here, does this come out a function? Remember the rule, if it fails the vertical line test, it's not a function, right? That means this would be very difficult to graph on my calculator. Not impossible, but difficult. If I wanted to graph it on my calculator, I'd have to put in y1 in function mode anyway. I'd have to put in y1 a square root and in y sub 2 a negative square root so that I get both pieces. Do you kind of remember talking about this before? For a sideways parabola. We can graph here, it says, we can graph curves that are not functions. So Monday we're going to graph some things that are ellipses and hyperbolas. Okay? Kind of fun. All right. For this first example, everybody awake? It says very specifically here we are to use t values from -3 to +4. I even gave you a little chart listing them from -3 to +4. It says the rule to find x values is to take -3 plus 4t, or 4t minus 3 if you want to write it that way. I don't care which way you write it. But I write it always above the x here because that's the rule that's going to get me the x values. The y values, it says over here to find y, I'm supposed to square t and add 3. So t squared plus 3. I write that rule up there so I remember how I got those values. Now when I go to plot them in a minute, t doesn't matter anymore. T helped me find x and y, but what I'm actually going to plot are only the xy ordered pairs. Does that kind of make sense, guys? Over here I only have an x and a y on my graph. All right, let's try this. It's kind of weird, but I usually do all the x's first because then I don't confuse myself. I just follow this rule 8 or 9 times or whatever I have to do. So multiply by 4 and subtract 3, and what will we get here? 4 times -3 is -12, minus 3 more is -15. Did I do that right? Yeah. Okay, what's the next one? -11, then -7, 4 times 0 minus 3 is -3. 4 minus 3 is 1. 8 minus 3 is 5. 12 minus 3 is 9. 16 minus 3 is 13. Did I do those right? Okay. Do I have ordered pairs I can plot? Not yet, because I only have x's. How do I find the y's? Yes, square the t and add 3. So 9 plus 3 is 12. 4 plus 3 is 7. -1 squared is 1. Plus 3 is 4. 1 plus 3 is 4 again. 7, 12, and 16 plus 3 is 19. Everybody okay with where we got those numbers? Now, we're going to plot them as xy ordered pairs. We're not even looking at the t anymore. The first one is at -15 and up 12. Found some freaky graph paper for you here. Try to make this work. -11, 7. Yeah, the graph paper the book gave was, well, 1 counted by 4s and 1 counted by 6s. You know how they do. It's just crazy. I was like, nope, not using that. All right, -7, 4. -3, 3. One, 4, 5, 7. Yeah, well, try doing it on this thing. It's even worse. All right, I'm not sure how accurate I was, but does everybody look something like that? Okay. This book doesn't talk about endpoints. Our old book talked about endpoints. The endpoints are very important. The values we get when we put in -3 for t, and the values we get when we put in 4 for t. Does that make sense, guys? Those were the 2 critical values on either end of the t, so those will determine the endpoints. So our endpoints are just -15, 12, and 13, 19. When you start doing these on your calculator, though, it gets really easy to forget where the endpoints are. Okay, they're the values of t is -3 and t is +4 for for this question, whatever the restrictions on the t are. All right, the thing our book does ask us to do is connect this with a smooth continuous curve, which of course will be a joke for Hofbauer. Well, that wasn't too bad. And then do what? Do you remember what else the book did? Put some little arrows to show what they called orientation, the direction we were going. So I don't know what this was supposed to represent. Okay, maybe it's the flight of a bird as it dove down to try to see if it could snap the mouse, and the mouse ran away, so it went back up in the air before it could catch it or whatever. Everybody okay? Now, the other thing besides plotting these you're going to have to do is you're going to have to write an equation for that graph in terms of x and y again. That's called, in our book, it's called write in rectangular form. It used to be, it would say eliminate the t. So in other words, get it back in terms of x and y. So don't need to do this one. Actually, I'm not going to even talk about this one. It does say here when you are doing this, you can eliminate the x. You can write t in terms of x and substitute it into the other one, or you can do it in terms of y and substitute it in. That'll make more sense after I show you what I'm talking about here. All right. This one is on your paper, and it's halfway done for you. So what they did is they took this one. It seemed a little easier because it didn't have a squared or a square root. They added the 2 over to the other side and then divided by 4 to get this. Is everybody okay with where that came from? Then they said, well, if t is equal to that mess, we can plug that in here, and we won't have a t anymore. So they have y equals that mess squared plus 1. Everybody okay? I would really be okay with this equation. I'm going to talk about rearranging it because this is not a form we're familiar with. 2 forms of parabolas we talked a lot about. Vertex form, and then in this chapter we did what's called conics or transformation form, conic form or standard form. So if we wanted vertex form, we could take and say I'm going to square the top and square the bottom. Does that seem okay, guys? And when you square the bottom, you get 16 down there, right? And because the top is in a parenthesis, could we write 1/16? X plus 2 squared plus 1. Everybody okay with what I did? Squared it, pulled it out front. This is the form we learned earlier this year, or back in Algebra 2. The vertex would be at -2, 1, and the 1/16 would make it, do you remember? Open up and wide. Okay. The form we used, okay, follow me here. The form we used recently, we would subtract the 1 over to the other side, so we'd have y minus 1. And then we actually moved this over to this side, so we'd multiply by 16. Does that look like what we've been doing recently? This would be 4p times y minus k equals x minus h squared. So this form is also good. Does it have the same vertex? hk is still -2, 1, right? Everybody good? All right, let's try this one. It's very similar. Very, very similar. But this is the one that goes with the example we just did a minute ago at the top of the page here. So if I rewrite this so that it says t equals, what will that say? Journey says x plus 3 divided by 4. Everybody okay with that? Then we're supposed to substitute that in here. So it will say y equals x plus 3 divided by 4 squared plus 3. Now, again, there's a 4 in the denominator. If we square it and pull it out front, it will become 1/16. Is everyone okay where I got the 16? Because I got rid of the squared on that part. So there's vertex form. What would it look like in, what did we call it last week? Conic form, standard form, rectangular form? I don't know what they called it. Conic form, I feel like, but y, yeah, 16y. You'd actually do y minus 3, subtract the 3 over there first, and then multiply by the 16. Does that look like what we did last week? Okay. Either one of those has a vertex where? Negative 3, 3. Because remember in this form it was x minus h plus k, and this one is x minus h and y minus k. Anyway, turns out negative 3, 3. Can you go back to number 1? Did it appear that this had a vertex at negative 3, 3? Yes. Okay. Everybody good that this is tying together for you? What? Okay. Oh, like a not. K-N-O-T. Gotcha. All right. Let's try this one. What is this giving us for t value? This is really important that you understand that this is not useless information. Sometimes in the past there was some inequality stuff at the back and we kind of ignored it. Okay, it might have been giving us something about a domain or something. We didn't worry too much about it. This is very important in this parametric business. It's telling us that the first endpoint occurs when t is negative 4 and the last one when t is positive 4. And if you want to generate values, there's some good numbers to pick. Now, we're going to talk about this in a minute. Your calculator literally does this one value at a time as well. So if we told it to count by ones, it would generate these same 9 values and plot them and connect them with a smooth curve, which is actually going to probably be a bunch of little straight lines. If you want it to get smoother, you put a smaller step in. Tell it to calculate 10 values in between negative 4 and negative 3. But you don't want it to calculate 1,000 values in between there because your calculator will take all day. No, not really, but it'll go very slowly. Talk more about that in a second. All right, how are we going to come up with x's? Square the t and add 4. So square the t would be 16 plus 4 is 20. How'd I do? Anybody have the next one? 13. 8, 5, 4, 5, 13. I got off, didn't I? 9 plus 4 is 13. 16 plus 4 is 20. Okay. Now, can I plot those? No, those are only x's. Now I need y's. How do I find the y's? I have to take half and subtract 3, or divide by 2 and subtract 3. Am I using 20? Be careful, these are all mistakes students make. Now I'm looking at these t values, right? Don't ignore the x's. Negative 4 divided by 2 is negative 2, minus 3 is negative 5. Did I get that one right? Okay, negative 3 divided by 2 is negative 1.5, minus 3 is negative 4.5. If you do a few, you might notice a pattern. Negative 4, negative 3.5, negative 3, negative 2.5, negative 2, negative 1.5, and negative 1, I think. Did I do that right? I think so. All right, now try plotting them. And what am I plotting? What's the end point? What are the end points? 20, negative 5 at this end at negative 4, and 20, negative 1 at the other end at positive 4. All right. 20, negative 5. Notice the x's are counting by, graph paper counts by 2s, 2, 4, 6, 8. But I changed it so the up and down is just counting by 1. Because they had it counting by 2s and it was so tiny you couldn't even graph it. Okay. 13. Negative 4.5. Whoops, I'm sorry. 8, negative 4. If you need to go get a drink, you can. All right. What do we have to do now? Connect it with a smooth curve and put some little arrows on to show that it went that way from the bottom to the top. Yes? Did I do it the right way, guys? All right. So the arrows show the orientation. The endpoints were at the two t-value restrictions, the greatest and least t-values. Is this a function when we graph it? No. If we tried to eliminate the t on this one, it would probably be easier to do it this way, right? The substitution, get the y solved, so you'd have y plus 3, and then you'd multiply it by 2 to get t, and you plug it in over here. You don't have to do this, I'm just showing you. X minus 4 equals, we square this and we'd get a 4 and a y plus 3 squared. Does that look like something whose vertex is 4, negative 3 and open sideways? HK would be 4, negative 3. Is that where our vertex is? The y is squared and it's a positive p, so it's opening this way. All right, you don't have to do that. I'm just trying to tie this all together. All right, ready to try the calculator? I really need you to be paying attention on this because I'm going to talk about some things, some mistakes you make, and the kind of the order you want to attack these in. The first thing, whoa, what did I click? Not what I wanted to. I want to click this guy. I'm still recording, right? Okay. What am I? Oh, dingbat. I want to click this. All right. I'm going to turn on the calculator, and I'm going to go to mode. Everybody with me? Under mode. We do need to be in degrees later today, so if you want to go down and make sure you're in degrees. But the important stuff for today is underneath degrees. There are 4 categories. It says function, PAR, which stands for parametric, POL, which is polar, and SEQ, which is sequence mode. In the next couple weeks, we're going to learn to do all of those. Okay? Parametric. Okay, before I go any further, look at the key we usually push to find x next to the green thing there. Do you notice it also has 4 things on it? X, t, theta, and n? Guess what? X is function mode, t is parametric mode, theta is in polar mode, and n is in sequence mode. So the mode you are in will determine what letter that button uses. All right, we are going to go with t in a minute here. The other thing is eventually you'll want this to be in simultaneous mode down here, sequential simultaneous. And you want it definitely today to be in connected mode. All right? The simultaneous won't matter today, and it'll probably reset itself for me anyway, because this calculator's kind of crazy. All right, 2 things. First of all, will you hit the window button real quick? We're going to come back to this button in a minute. But you notice right away it asks you for a T, min and max, and T step. All 3 of those things are important. The T, min, and max for this question are going to be what? 0 to 9 from right up here. So you can type T min 0, T max 9. The T step, I said this earlier, please listen closely. That's how many times the calculator calculates something to graph. From 0 to 9 is like 10 values. I could leave the t-step at 1 and it would calculate 10 values and connect them with straight lines. If I wanted to leave it 1/10, that's like 10 times in between those, so I get like 100 values connected with a nice smooth curve. That's great. If you want to play around and have fun one day, change this to like 2. Then it's only going to calculate like 4 values and connect them with straight lines. You're not going to see a smooth curve and you're going to get all confused. Better yet, put in a 9. How many times between 0 and 9? 1 value. Is that going to give you any kind of a curve? No. So if you aren't getting anything, it could be that your t-step is messed up. I'll just tell you this. For this class, just use 0.1. Okay, just use 0.1. It's all good. Second thing I want you to do is hit your X button, or your Y equals button. I'm sorry, Y equals. Now I got some crazy business in here. This says put X, enter an X equation in terms of T, and then a Y equation in terms of T. So for X, we're going to type T divided by 2. I'm going to scroll down or hit enter. And for Y, we're going to put the square root of T plus 2. And if you have the older calculator, you have to close the parenthesis. The newer ones, you just go out of the little box to put your plus 2. Everybody getting where to get the T? Everybody's doing this. Those of you who aren't doing this, don't ask me later because this is the time. Everybody okay? All right. Before we do anything else, will you look at the table? So go second graph and look at the table. We are only concerned really with values of T from 0 to 9. Notice the calculator calculates more than that, okay, on the table. So it's going to graph. I need to know how to set up my X and Y window, so I want to look at the values. By pulling up the table, I can tell how to set my X and Y window. My X values go from like 0 to 5, and my Y values also go from like 2 to 5. So I'm going to go back to window. Everybody with me? Window. Go down to this X min and put 0. Max, I'm just going to pick 6. For scale, I'm going to use 1. Scale on X and Y doesn't really matter. Y min 0. Y max 6. Y scale 1. All right, last time I'm going through this, I have from the top 0, 9.1, 0, 6, 1, 0, 6, 1. Now I'm going to hit graph. Who's is not getting that shape and graph? We're all good? All right, this is the curious part for parametrics. When you hit trace, you get 3 variables on the screen. But the only one you can control with your left and right arrows are the T. You can only change the T values. The X and Y values are calculated based on that T. If you want to know what T is at 1.443, okay, you have to either type 1.443 for T, and then it would calculate the X's and the Y's. Or you could go second trace and go here and enter in a value. Look at what second trace says. dy dx, dy dt, dx dt. Anybody ever heard of those? Calculus. If you have any of your friends who are taking calculus, what? Yep, those are derivatives. Okay? You use those in calculus. For today, we're just going to use T. All right, let's quickly do this one. If you want to know where the points are to plot them on nicely on your graph paper, go back here. It said at t equals 0, we had an end point at 0, 2. Anybody scroll down to 9? What was the end point at 9? 4.55. All right, and if you want to graph, you can plot these points. I'm going to just do a few of them here. Like, what was it? At 0, we had 0, 2. At t equals 4, it was at 2, 4. Uh, 4.5 over, it's up at 5. All right, I'm lazy, so I'm just doing a couple of them because I already saw what shape it was. All right, and it did go up this way, right? Looks almost linear on my graph paper, but it's because I only plotted a couple points. Everybody okay? Any questions about using the calculator to do these? All right, can we practice eliminating a t real quick, and then we're going to do our application. Who wants to do number 3? Anybody tell me what to do? What do you want to do, Ben?
Right, so on the x part, you just subtract 3 and then divide by 2.
Okay.
Right, and then you take that value, so you put in your y in that t, so y equals x minus 3 over 2 or minus 2.
Okay, is that a parabola, guys? No. As a matter of fact, it's what? It's a line. It only has, if I simplified this, I would get 1/2 x minus 3 halves minus 4, which is 5.5. Or 11 halves back there. No, we don't want to square it. We don't want a parabola. We just want to leave it alone. Okay? This one is a line. On this, the other, I just want to show you this. This one might have almost been easier to do the other way. Everybody watching? Could I make this say y plus 4 equals t? And then I could have put it in over here, so it said x equals 2 times y plus 4 plus 3. But that's kind of messy equation of a line, right? If I distributed and subtracted the y over there, I'd get 8. There's a standard form equation. If I rearrange that, guess what it would become? The same as that one, okay? So it doesn't really matter what, as long as you get rid of the t, I'll be okay with it. What do you want to do on this one? This one's pretty easy. Nobody? So we have x minus 5 equals t, and then we could just plug that in here. So we have negative 3 times the quantity x minus 5 squared. Does that look like something you could type in graph? In rectangular mode or in regular function mode? It would be a parabola that opened. Take your brain back to algebra 2. This is just a parabola that opened down and is skinny, right? You foiled it all out? Is that what you said?
Yeah.
Yep, you absolutely could. Doesn't sound fun to me, but yes, you could. No, you're good. As long as you've gotten rid of the t, I'll be all right. All right, that is actually where your homework ends, I think. Okay, actually, if I go to the end of this, it says, does your sheet at the bottom say 32 and 33? Okay, those are applications. If you don't get that far, we're going to go over those, some more application practice on Monday. If you at least get through the 15 odd, you get the easy ones done. But I want to talk about these. All right. You do something similar to this in physics. How many of you are in physics? Oh, awesome. This class has a lot. Okay. It's probably a little bit different than it is in physics. Of course, you know, math and science can never get their acts together and do it exactly the same way. But this concept is talking about when you throw an object with an initial velocity in a particular direction, an angle to the horizon. Much more realistic than when we talked about throwing a ball straight up in the air and having it come back down, right? Does everybody know what I'm talking about? In Algebra 2, you did those throw-up problems, even if earlier this year. What's the height of the ball after this many seconds? Blah, blah, blah. Well, this is much more realistic because there's some kind of forward motion. All right, the equation we're going to use, this is what I want you to see. X is going to be t times initial velocity times the cosine of an angle. Please notice cosine goes with x. It's also going to have in the y equation t times initial velocity times the sine. Sine goes with y. Does that sound familiar? All right. The actual formula says -1/2 g t squared. As long as we're in feet per second, it's just -16. I think when you do meters per second, it's -9.8 or something. We'll worry about it next week. All right, I'm going to do this one really fast. Just watch because it's kind of fun. You can type it in with me if you want, but it says Kaylee's practicing free throws for an upcoming basketball game. She releases the ball with an initial velocity of 24 feet per second. That's v sub 0, everybody, okay? At an angle of 53 degrees with the horizontal, that's theta. Horizontal distance from the free throw line to the rim is 13 feet. That doesn't go into our equation, but it's going to help us later. The vertical distance from the floor to the rim is 10 feet. That's up and down. Again, doesn't go into our equation. It's going to help us later. The front of the rim is 2 feet from the backboard. She releases the shot 4.75 feet from the ground. That is h sub 0. So this is what I would type in my calculator if you want to try this. X equals, I would do t times initial velocity times cosine of the angle. And then I would do y equals, and it's feet, so I'm going to go -16t squared plus t times 24 times the sine of 53 plus, how high was this when she let go of it? 4.75. Okay, kind of off the screen there. If you want to try typing this in with me for practice, you don't have to. But I'm going to go x equals t times 24 times the cosine of 53 and -16t squared plus t times 24 times the sine of 53 plus 4.75. All right, if I do nothing else and I just go to graph, I actually got an error. I might have typed something in wrong. I put a minus instead of a negative. I don't see much, do I? Okay. Let's think about what's going on here. Does it take 9 seconds for a free throw ball to come down from the time it leaves your fingers? No. If I look at the table of values, this will help determine my window always. Times 0, it's 4.75 feet up in the air. By 2 seconds in, it's underground, -21 feet. It's a very powerful throw, okay? Basically, after 2 seconds, it isn't going to matter what the height is because it's already hit the floor. So I could make my t 0 to, I'm going to just change it to 3 and leave it because we're going to need it for another example here. But again, that doesn't really help. Obviously, the ball goes further away. If I go to the table of values again, the x gets very quickly up to like 40. And the y gets up to, I don't think it goes up to like 8, but I'm going to go a little bit higher than that, okay? So I'm going to go 0 to 40 for my x max. And my y, I'm going to go 0 to 10 just to be safe. I think that's safe. Nope, not safe. All right, my y, I'm going to do 0 to 20. All right, so here's the path of the basketball. This means nothing to us. If I trace along, here's the ball at every point in time. The question is, does she make it? Well, what do we know? How far is the basket away? 13 feet. Is that an X or a Y? X. It's an X. So if I go out until X is 13, here, I'm stopping right here. It's hard to see, but it says 12.999. It's 0.9 seconds, but the interesting part is y equals 9.0. How tall is the basket? 10 feet. If the ball's only 9 feet up at that point, did she make it?
No.
Air ball, right?
No. It's under the basket.
It's underneath the basket, yeah. Okay. Right. Michaela would never do this. Okay. All right, we're going to go to the next question because I like this one. I asked you a whole bunch of really fun stuff. Everybody's going to try this. Ready? It's fun. Okay. The initial, we're going to put in T. Initial velocity is what? Anybody read about Luigi? 35. Cosine of the angle, which is 48. It's in feet per second, so we're going to do negative 16t squared plus t times 35 times sine of 48. Plus, how high was the ball when he kicked it? 2 feet. Okay. Everybody got what they're going to type in? How long do you think it takes soccer ball to come down? I think 3 seconds is plenty, so I'm going to do 0 to 3. I don't remember how far this goes away. X is how far away. I might try 50 to start. And Y is how high it goes. I think I'm going to leave that 0 to 20. All right, get that all typed in and see if the ball hits the ground in that window and all that good stuff. And then I'll tell you how to answer all these crazy questions it asks. Oh, did I change my window? I don't even remember. 0 to 3, 0 to 50, and 0 to 20 actually works just fine. All right. I'm only allowed by tracing to change the time. The questions I've asked here say find the time the ball hits the ground. So what do I want to have happen when I'm tracing? Hits the ground means what? 0 for X or Y? So as I trace along, the closest I can get to 0 is negative 0.02, yes? How long did it take to get there? Anybody get 1.7?
Yeah.
At t equals 1.7, it's hitting the ground. How far away is it?
40 feet. 39.8.
What happened to my cursor? The x is how far away it is, so it's 39.8 feet away. Now trace backwards and see if you can get an estimate on how high it went. What's the maximum y value?
12.56.
About 12.6 is as high as it ever goes. Everybody see what we're talking about for y? This is a fun question. Okay. There's a defender spanning 35 feet away. Where do I want 35 to be? So I'm going to cursor around until I get x pretty close to 35. What is the height of the ball at that time?
5 feet.
5 feet up. 5 feet up at 35 feet away. So does it clear the defender? Does it go over his head? Probably nails him right in the face, right? All right.
Whoa.
Next week we'll do something fun. Maybe one day, a Monday, like draw in the defender. Let me see if I can remember how to do that. Which one's the draw menu, guys? I can't see. Oh, this one. Okay, here's my fun. Ready? There's the defender. Oh, he was supposed to be 6 feet tall, wasn't he? So I need to redo this and make it 6 feet. If I put him in at 6 feet tall, it'll draw the defender and hopefully hit him in the face. I hit enter. There he goes. He's getting slammed. All right, guys, so finish the assignment at least through number 15 here and work on that packet. Any questions?